Good evening, everybody. Good evening, everybody. Yeah, that's a David Blank Edelman sort of thing. He's one of our coworkers here at Apcera, and he's basically the one who's been teaching us all how to speak well. So I haven't learned quite well enough yet, but I did learn one trick. So my name is Alex Toombs. I'm an engineer here at Apcera, and I've been here for about 3 years, a little over that. And my background is in electrical engineering. I moved into the exciting world of enterprise software, container space, kind of right at the inflection point, right when Docker became open source. So very interesting time to be in the space. And let's see, I want to zoom out a little bit. You can get the title that way. So I built on most of the parts of the Apcera platform, especially the core area. So here at Apcera, we're providing a platform for people to deploy and manage their applications in containers. That's sort of the connection with us and Docker, and I'll talk a little bit more about that. But this talk is not about Apcera. It's more about Docker and the Docker Registry. So I've worked a lot on Docker, containers, the packaging system, and now I'm working a little bit more with Kubernetes, as well as Karma, which is our open source container runtime based off of libcontainer, and a little bit of other work. So I'm going to run through some stuff. I'll start out with a little bit of an introduction of containers and Docker images, how we map them into our system, a little bit about what we do. Again, just 1 or 2 slides, and kind of run through how you integrate with the Docker Registry API and the challenges that people face when running Docker images without running Docker himself. And also, this talk here is running on our platform. We're a platform, so I had to do that. I mean, that's about as nice of a URL as I could have made. It's a lot longer if you look at my URL bar, my address bar. So if you want to, you can go there and follow along. If not, I'll do it. So, all right, containers. It's Containers 101. So maybe a little bit of an intro. Containers, they're process level isolation. So basically, the base elements of that are C groups for controlling resources and namespaces for isolating the view of the world of the application running within the container. So these are just Linux kernel features, and they're inspired and originate from FreeBSD jails and Solaris zones. And Robert did a much better job going into the history than I will do here. So this is really just a brief overview, a picture of what that looks like. So you have container, you have some binaries and libraries in each of those containers. They're running, this is an LXC example, so something that is generic, not focused on Docker, using LXC as the execution environment, which is what Docker was originally based off of. It's running on top of a host OS, which is running Linux, and it's running on top of some sort of server. So a little bit about confusion. People mean a lot of things when they say containers, or can mean a lot of different things when they say containers. It can also mean container images, like Docker images. It can also mean the runtime or other Docker things. So, right now we're going to be focusing largely on Docker images. So, Docker, great company. They have been around since 2004 as .cloud, and recently as 2013, open sourced their container runtime as Docker, and that's taken off in a huge way and really brought containers to the masses. That's part of why we're all here right now. So the high-level goal is build, ship, run any app anywhere, and they brought containers to the masses, like I said, with great developer tools. So they started out as PaaS, and they've been leveraging Linux containers for isolation of the apps, way back, even before 2013. So what do? They ship containers or they run containers? They really do both, and a lot of other things. They have a lot of different tools that they can post together. They have the engine, which is the Docker daemon. It's called a lot of different things. They have Compose. They have Swarm for clustering, and they have the registries. All these things fit together, plus other stuff, to make the Docker data center, which is sort of the composite platform. So this talk is really about Docker and other platforms. Because Docker has become such a popular image format where people want to package their application in Docker image and bring it to whatever their company chooses to run something in production, drop it in, people have been kind of scrambling to support Docker images. So containers mean multiple things, and Docker means many, many different things. So Docker support is really an interesting topic. So in comes Apcera. Like I said, just a brief couple slides. We're a container-based platform software. Lots of commonalities with Cloud Foundry. In fact, our founder was one of the first people building Cloud Foundry at VMware. Common as OpenShift from Red Hat, Mesosphere, Docker Data Center, and we've been using Linux containers for isolation since 2012, about late 2012. So the Docker engine launch was in March 2013, I think, and we've kind of been developing our own in-house container solution since then. Now, going back to the beginning, this is still based off of C groups and namespaces, so there's no magic here, same sort of stuff. And we are developing a libcontainer-based Apcera implementation, Karma. So I'll talk a little more about this later, but you have libcontainer, which was donated by Docker to the Open Container Initiative as the base element for creating containers. And you have AppC, which is a spec for containers, runtime, image, and discovery by CoreOS. And we're kind of mapping the two. So we're taking the parts we like best from both. So we're using libcontainer to get a lot of the functionality that Docker has. And we are developing something that's AppC compliant. So this is really just a brief overview of our architecture. It's pretty simple. You know, you have, I'm kind of joking with that one. It's got a lot of different boxes here. So API server, you send a request, eventually it runs a job, and that's running inside of a container. So anyways, these slides will be available. If you guys want to check them out later, I'll keep the application up and running. So Apcera and Docker. Apcera jobs, Docker images. So our terms aren't a one-to-one map. We are a separate platform. So we have levels of abstraction of packages, which are kind of the what of the app, and jobs, which are the how. And then instances kind of map to containers. So when something is up and running and there's a container allocated to run that process, that's an instance. Whereas with Docker, you really have images and containers. So Apcera jobs are templates for those instances, and Docker images contain both the runtime metadata and the app content. So we respect both of those, both the runtime metadata and the application content, as much as we can. So again, reiterating, we pull Docker images, but we do not use any part of Docker. And that's bolded down there. No Docker components are running as part of our platform. There's no Docker engine, no Docker Compose, no Swarm, nothing like that. A little bit of Docker code is used here or there for content digests, registry authentication, but other than that, it's all in-house. The Docker images, brief overview of their format, what they look like, what they're made out of, and how that matters to a container. Why does this thing work so well? So they're hosted on a Docker registry, downloaded by the Docker engine or by another platform, such as the Apcera platform. And they're pointers to a bunch of file system layers. Now, each of those IDs are content digests. So basically, the name of the layer is a hash of the digest, of the content of the layer, rather. So content addressable file system. We'll get into that part a little later. And layers may be shared between multiple images. That comes down to you saving space and time, because you don't have to download the same content twice. They're built by Docker's build tools. Most people don't try to re-implement Docker build. They just use Docker itself. Docker files go in, images come out. And they're really a de facto standard, but they're not a standard. And that's part of the issue with running Docker images without Docker. So this is a brief overview of what that looks like. You have a thin rewrite layer that is created on top when you layer something into the container. And then you have a bunch of read-only mounted layers. And this is taking advantage of copy on write. So the layers are mounted as read-only so that we can reuse them between multiple containers using the same content on the same host. Copy on write means that multiple containers can share that layer, and they only copy if modifying the content. So in the case where we're only writing new files, we're not modifying anything that was there originally when our app started up. We're not making any copies of any of the content that was layered into our containers. The read-write layer is where everything else that's new goes. So for us, what it means to pull in a Docker image means that we map the image to packages. So we map layers to a construct called package resources, tarballs, fancy word for tarballs. We copy the runtime metadata, like memory, start command, et cetera, to the job definition, and we map a container to an instance. So Docker images without Docker, this is the title of the talk. It's kind of like in a Bond movie, you know, where they say the Bond movie title. It's that sort of thing. So you want to run Docker images, right? So step 1, fetching an image from a registry. Step 2, you create a container. Step 3, you mount the layers into a container using a layered file system. And step 4, you start the container. So I'm going to go step by step and kind of explain each of these in a little more detail. Fetching from a Docker registry. The Docker registry serves images. These are pushed by users. You can have the public Docker Hub. You can have Quay. You can have a private registry, Amazon ECR, Google Container Registry, private variants, et cetera, et cetera. The API is standard by Docker as the Docker HTTP Registry API v2. The v1 was deprecated in December 2015 in kind of a serious way. So the Docker Hub and other registries expose an HTTP API for serving two things, images and blobs pretty much. Some other stuff in there, but images are a JSON manifest of what you need to download and how you run it, basically. And the blobs itself are indicated in the image by the content digests of each layer. So blobs are layers, that's what it's called in the API. So like I said earlier, content digests are a way to address content by the name, by the content itself. You know, the name of it is whatever's inside of it. Registries have multiple versions, like I said, and registries can implement multiple versions of the API, so clients should be able to fall back to the v1 registry API when necessary. So basically, a client has to check to see if it's v2 supported, if not, fall back, etc. As an aside, they deprecated the support for the V1 registry back in December 2015. That actually bit us because there was about 4 weeks notice of doing that. So we had to kind of scramble and implement V2 registry support. And it's still a big note at the top of our documentation that if you're using Apcera platform version prior to such and such, it's not going to work anymore. Sorry. So we didn't get a whole lot of grace period on that. Some registries still support V1. We still support V1. Docker client still supports the V1 Registry API. Most of the content in here refers to the V2 Registry API. In terms of talking about authentication later on, in terms of the image structure, those things have changed. In fact, the content addressable component didn't come into place until the V2 Registry API. So authenticating, if you want to fetch a Docker image, you need to be authenticated. There's scope to a repository, and you get one token required per each call against the registry. So it's a challenge and response mechanism. And in fact, to see if the registry supports V2 API, you actually need a token. So you can't even check to see whether or not it supports the V2 API unless you are authenticated, which is a little annoying. You get a 401 when you try to curl like this. And it gives you back this authenticate header with some other stuff in it, a realm, a service. From here, you need to make another request, get an authentication token. It's just a long bearer token. And this allows you to make a subsequent request. And you do this for every time you need to check something. When you fetch an image, you need a token. When you fetch a layer, you need a token. And these can be scoped. So you can say, I only want this to apply to a specific repository that I plan on pulling, a specific image. You can also authenticate with a token for a specific action, like push or pull. And the authentication scheme differs per registry. So Quay and Amazon ECR are two examples where they have their own authentication mechanisms. They're sort of in addition to Docker's authentication mechanism. So that's another challenge of being somebody who's implementing a registry client without actually being Docker. All these registries are building such that Docker works with them, but we're kind of coming in after the fact and having to support multiple things by doing a little bit of work each time. So creating a container, you download something, you want to create a Linux container, right? So just C groups, namespaces, we're already experts in that one. You pivot root to move the root file system of the current process, and then you're done. Here's a snippet of code. For those of you who want to learn more about writing your own container runtime, there's a great InfoQ article, sourced down here, basically how to build a container in Go, and this is a snippet from that. So I'll share these slides, the link is down at the bottom, and I'll be using some more examples from this. But basically this is creating a command, setting some different namespaces, so you can see new ETS, new PID, and basically creating new namespaces. And that is a way of isolating whatever command we're about to run. Mounting layers. So you have an image, it has layers, and you want them in your container, right? So you stack them one on top of another until you get something that works. AUFS, OverlayFS, ButterFS are all around to give your containers content. And going back to copy on write, basically it allows you to efficiently share that content unless you need to modify the other underlying content. So because Docker image layers often share between multiple images, for instance, you may have an Ubuntu image and a Ruby image that have 2 or 3 layers in common, it means that when you run both of those in your host, you only need to download whatever layers are not in common when you run the second image, which is nice. And sharing's caring, right? So starting a container. So again, this is an example from that InfoQ article. I recommend it. It's a really great kind of overview of how this works and how to write one yourself. So you can start your own Docker competitor overnight. So this is just starting a container. You're calling pivot root, and you're running a command. You set up isolation. Now you run your app. The app believes it has full access, but in fact, it's limited by the namespaces that are around it, and its resource utilization is limited by C groups. For instance, if you set a memory C group, then if the application exceeds its memory allocation, the kernel will actually kill it. So that's just one way of making sure that people don't exceed whatever boundaries they have. So how well does this work? So there was actually a really interesting Twitter kind of war that raged maybe 10, 14 days ago, something like that. Kelsey Hightower, he's a developer evangelist, formerly at CoreOS, now at Google working on Kubernetes, kind of called out Solomon and Docker for not contributing much to the Open Container Initiative image spec. The thing is here, though, that Solomon kind of responding is saying that platforms that are supporting Docker images only can support maybe 90% of Docker images or 90% of the functionality of a Docker image. That's true across all platforms. You look at Cloud Foundry, and they don't have support for private registries. They don't have support for a number of things. It's enabled via feature flag. With us, there are certain things that don't work. I'll talk about those a little later in more detail. But basically, Docker's argument is that they're moving very quickly, and they don't want to have to standardize. So again, Solomon's point is here is that all these platforms out there that are implementing Docker support have partial and broken Docker support because the platform is moving so quickly. You can even see breakages between different versions of Docker where the existing image will no longer work. So it's a reality of a fast-moving project. It's something kind of unique about Docker. Being in the enterprise space, a lot of times people become very reticent to change because they don't want to take down customer applications. Docker has chosen a little differently of a path there. So that means they continue to innovate very quickly. Many platforms claim Docker support. Most really mean Docker image support. So that's true of us. We claim Docker image support. We're running Docker images. We don't claim to support Docker Swarm, anything like that. But the lack of standardization means that a given Docker image may break. It's not like all of your Docker images will stop running overnight, but let's say someone republishes something, changes a little bit, maybe in the entry point script here or there, and then all of a sudden, what you wanted to work no longer works. So I talked about this earlier, but the V1 Registry API got deprecated with very little notice, about a month. So this was an email I received from Docker, kind of letting me know that. It was the second reminder, but I don't think I ever received the first reminder. Letting us know that the Docker Registry API was going to be deprecated, the one that we were using. So it is a little disappointing. We had to, as a software provider rather than a service provider, puts us in a kind of unique position. We had to ship a new version of our software out and encourage our customers to update and get new trial versions out to everybody, as well as implement all this different stuff. So it adds lead time on being a software provider rather than a service provider. So it was just kind of a quick fire drill. Nothing too crazy. There weren't wildly different registry APIs. They're still downloading tarballs and fetching JSON metadata. But it was something that wasn't great to have to do. So here's a few examples of different breakages. This is something that has hit us before. So Docker's interactive mode works by streaming standard out and standard in over an API, and then allowing your local shell to attach to those processes. It's via Docker attach or Docker run-it for interactive mode. Basically, we don't use that. We use SSH. So we run SSH alongside the containers. And we use our policy system to prevent people from accessing the SSH daemon unless they have the required policy to do that. So Docker started republishing not only the new versions of their official images, but also the old tags of those official images with locked root user accounts. Now with Docker, this makes sense as a bit to increase the security of those images. It's something that Docker's kind of hit on a lot in the past. But in our case, that means you can't run SSH. So we had to work around that. We had to essentially unlock those root user accounts. Because we have user namespaces on by default, it's not a huge deal. We have a lot of other security features, our policy system, as well as all of our different levels of authentication prevent you from accessing that. But it's just something that is difficult to kind of work around and to see when your Docker pulls start failing, or stop working. Different authentication mechanisms. So I talked about this a little bit earlier, but a variety of different registries from all across the span of things. You have Amazon ECR, you have Google Container Registry, Quay, and Quay Enterprise, which is the private variant. It costs a lot of money. All these things have different authentication strategies. Some are OAuth compliant, some just use username and password. And like I said earlier, when the developers are building these things, rightly so, they go to Docker and they do Docker run against some registry. And if that works, they say, OK, cool. The problem is if you try to come in later and implement against the spec, they may not be up to spec. In fact, with Quay, for instance, there was just an issue, some minor thing. I forget exactly what it was, but it required an update to Quay to be pushed out for it to be in compliance with the spec. So it's just one of the difficulties of coming in and kind of being someone who's catching up on running these sorts of images. So same sorts of challenges that you'll see Mesosphere facing. In fact, Mesos is now trying to work around some of this stuff, not Mesosphere themselves, but Mesos released another way of running Docker images without Docker, just using basic Linux container primitives rather than actually running the Docker engine under the hood. So the bottom line is that the lack of Docker image standardization means things can change really whenever. It's not like there's some sort of spec that they've agreed to comply to. It's not something that we can really expect to stay static, that we can really keep working against. And it sets up bad experiences for users. They expect that whatever image they publish is going to continue working going forward. If Docker releases a new update, it no longer works on Docker on the Docker daemon itself, or if something is republished like an official image that someone depends on in their CI system, it's difficult, and especially with the use of the latest tag. Docker's been trying to tell people don't use the latest tag because it gets republished all the time. It's really not a great idea to use, but it's very convenient to use, and it's the default in all sorts of platforms, including ours. So it's something to be aware of. So what should we do about this? Standardize. That's really the answer. Last June, in fact, in response to a lot of kind of the growing noise around people complaining about Docker's lack of standardization. At DockerCon in June, Solomon went on stage and announced with Alex Polvi, the CoreOS CEO, that they were launching this open container initiative. So here at Apcera, we're founding partners of that. Amazon, Google, CoreOS, Docker, you name it. Basically, everyone who's anyone in the container space, it has some presence in there. And they made a lot of progress on the runtime definition. So Docker engine has actually changed a lot under the hood, even though you can't really see that as an end user. They donated their container runtime, libcontainer, which I mentioned earlier, and the reference implementation that wraps around that, called runc, that's all donated to the Open Container Initiative. So they've contributed a significant amount to the runtime definition. CoreOS, Red Hat, also huge players behind there, on there all the time. You can see them opening pull requests. You can see them having weekly meetings and mailing threads. I highly encourage everyone to take a look at those on opencontainers.org. But the image standard has really sort of been lacking, and that was what sparked this sort of Twitter debate a few weeks ago. So active development is beginning, though. Especially CoreOS and Red Hat have been the two biggest players behind that. And there is the person in charge of the registry development at Docker. I think his name's Stephen Day. He's been contributing to that as well. So you're starting to see these things kind of come together. It's difficult, though. If you have people depending upon app container images, on Docker images, on having a standard when these two things keep evolving in tandem, or in parallel rather, not really kind of overlapping with one another, it's difficult for the middle to get any sort of significant adoption when none of the container runtimes support it. So it's really in the early ground stages, and people who are interested in this, I highly encourage everyone to get involved to contributing it. So like I said, help contribute. This is a link to the image spec. We can even go check it out right now, assuming I have internet. Open Containers, a GitHub organization. The image spec is here. You can check out why they want to do this. You know, that's one of the first things in the FAQ. Why doesn't it mention distribution? They talk about how to kind of segment a lot of these concerns, because in a lot of ways it makes sense for Docker to want to control the distribution of images. They're not even trying to replace, say, the Docker Registry or Apcea's discovery protocol. They're just trying to have a common bundle that can be distributed in any sort of way, and then that any container image can expect, or any container runtime can expect to receive and run in a pretty similar fashion. So this work started about a year ago, or the repos were created about a year ago, and it's really been slow going. So I think we want to hope that we'll have a brighter tomorrow, and that we'll have more compatibility, more standardization, and more cooperation across the space going forward, because that's what you sort of need to carry the ball forward more.